All right, so what have you learned so far? We have learned so far how to build a language model. And what was a language model? Language model is a black box that tells us how likely or how probable any given sequence or the sentence is under the data set that we use to train this black box that is a language model. And then the reason why we focused a lot on that was because first, language model seems to encapsulate a lot of problems that we want to solve anyway. And that's only natural because natural language or the language is how we in fact convey ideas from one to another. And then that conveying the idea from one to another is precisely what machine learning is supposed to solve, that is to answer some questions. So in that sense, language model is very powerful because we can, frame any sophisticated high level, low level, or the very broad or narrow questions or the problems that we want to solve into natural language. Now, of course, the second reason was that the language model seems to be one thing that is extremely fundamental beyond usual text classification. So what made language models somewhat different from text classification? In the case of text classification, the idea was to try to identify one of small number of categories or classes to which the input sequence belongs. Right? So that was the idea. But now, if you think about what language model does, in particular from the perspective of the autoregressive model, given one sentence, we actually create many different problems. We're creating as many text classification problems as there are words in the sentence. And that actually does make things a bit more complicated. In what sense does it make it more complicated? Let's say I want to do the classification of any given, let's say, Amazon review or the eBay review. If anybody actually writes reviews on eBay review to be either positive or negative about the product, I can immediately tell based on what my model tells me whether this review is positive or negative, with a kind of full trust in our model. But then let's say we want to use the language model. Let's say we're talking about the autoregressive model with a left to right ordering that has been fixed. And then what I want to do is that after seeing the first half of the review, I want my language model to be able to tell me what is the most likely way to finish off this review. Now, when doing so, you can imagine that, this is in some sense pretty similar to text classification because there are indeed, assuming that there is a maximum max length that has been predefined, there are indeed a finite number of possible endings. So all we are doing is to figure out to which one of all those endings this prefix of the review belongs. Right? That's the problem that we're solving. But obviously the issue is that it is many. There are exponentially many possible so-called endings or the categories with respect to the length of those endings. And then one thing you always need to keep in your mind is that when you are dealing with this kind of, let's say, exponential number of possibilities or the combinatorial space, you need to pretty much stay away from it. That's not the problem that you want to solve. So, but then of course, what we're going to learn today is how we can use language model in order to solve this problem, at least approximately, with the level of the quality that is in fact acceptable. So in that sense, language model is really important because this actually gives us a way to think about machine learning, the kind of class or the family of the problems that we can tackle with machine learning beyond usual classification. Now, unfortunate thing about language modeling is that although it looks like it's something that is so generic that it can actually be used to solve any problem that we want, and then we know how to train it, and then it looks like the training does not require any kind of label data, so it's easy to get the data to train the model. It looks like everything is great, except that it's not really a problem on its own. So language modeling is not a problem. Why would you ever want to actually know the probability that my language model assigns to any arbitrary text? What does the probability even mean? If you think about the probability in a very naive way as in so the probability of, let's say my coin landing head is, let's say 75%, If you want to do a frequent test, you're going to say, oh, if I toss it 100 times, 75% time, right, I'm going to see the heads. If you're Bayesian, the probably 75% means that you had some prior conviction that the things is even between, let's say, heads and tail, but there is some, let's say, mysterious thing that we couldn't account for that actually makes the probability of this coin landing heads a bit higher than 0.5. So when there are two possibilities, okay, pretty clear, we know how to interpret it. Now, in the case of the language model defines a distribution over all possible text. Let's say we're going to only consider a sentence. Even then, the length of the sentence can be arbitrary. I don't know how much you are into those magical realism from the South American authors. Sometimes one sentence goes for, let's say, 5 to 10 pages long. True story, by the way, yes. If you look into the, what was it, the 100 Years of Solitude, there is one sentence that's about 2 pages long, 3 pages long. It's a very long sentence, right? And then now my language model should be able to assign a probability on that one as well. Let's say there was about 2,000 words. Now what that means is that the number of all possible sentences I can get, or the number of the all possible 2,000 word long sentences I'm going to get, assuming that my vocabulary is only a million, although often it's actually greater than, it's going to be million to the power of 2,000. That's already greater than the number of atoms in the entire universe, or this visible universe. What that means is that the probability that we're going to assign tends to be tiny, 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 because they all have to sum to 1. Right? So the probabilities that we're going to distribute over this, let's say, the number of the possible sentences that actually is greater than the number of the all atoms in the universe need to sum to 1. So what that means is that we can't really interpret what it means for any particular probability that is given by our language model, because it doesn't really tell me anything. So what is the 1 out of the million to the power of 15 versus, let's say, 1 out of the million to the power of, let's say, 14.95? Doesn't really tell us much, right? So in other words, language modeling, conceptually really nice, but it's pretty much useless in general. And in particular, especially if you start thinking about how many examples, training examples you're going to use in order to estimate those parameters. And then this goes back to our discussion on the anagram language model, particularly count-based one, where we are essentially creating this gigantic table. Each row corresponds to each and every possible sentence. And then we're trying to estimate how often they will appear. And then this table has a million to the power of 2,000 rows, while the number of examples that we'll get with the length 2,000 sentence is essentially 1. How are we supposed to estimate all those probabilities? It's actually impossible. So it makes language modeling a bit of a, I would say, conceptually nice, but not really a real problem. So let's jump on to some real problem that we can solve with the language model. In particular, one way we're going to do is to make the language model conditional. So what do I mean by making the language model conditional? Is actually very straightforward. So we're going to stick to the definition of the conditional probability. What language model computed was P of y, where y is some sequence y1, y2, and then yt, say t. But then what we're going to do is we're going to turn this into P of y given x. And then where x can be in fact anything, so we're going to consider the problem of translation. So we're going to say that the x is a sentence written in another language. And then this condition, so the conditional part on this next. And then what you see is that because we don't need to compute the probability of x, but we only need to compute the probability of y given x. But the means is that we're not actually predicting x. So what this actually tells us is that we already know how to build this model. But before getting into the model construction part that we're going to do as a kind of, let's say, mental experiment or the exercise. But the reason why this makes the problem much more interesting and real compared to the usual language model that is trying to estimate the P of y directly is that Here, why? The probabilities are generally too low. And then mostly they have to be low. You cannot have a very high probability sequence or the text under generic language model, because there are just so many sentences that are well formed and valid. On the other hand, as soon as we condition the whole thing on something that we see, right? Sometimes people would call it grounding. Sometimes people are going to call it conditioning. Sometimes people are going to call it contextualization. Is that once you're given some context, then the number of possible sentences that make sense under that context dramatically reduces. Now, in the case of the problem of machine translation, which is the one that we're going to look into more in detail today, in the case of machine translation, the goal is to define a distribution or compute the distribution over all possible translations y, given the source sentence x. And then how should this distribution look like? Is it under this distribution or under this conditional distribution, the correct translation of the source sentence x should have a high probability. Now I'm saying a correct translation because we are again getting into this kind of, let's say, the part of machine learning where we are not anymore assuming that there is a one correct answer given some. Then that's true for the problem of machine translation, as well as almost any interesting problems that are beyond classification. Given any, let's say, sentence in any language if you are asked to translate that to another language that you will notice that there are a lot of different ways in which you can convey exactly the same meaning that was supposed to be conveyed by the source sentence. However, at the same time, the number of possible correct translation is still dramatically smaller than the number of all possible well-formed valid sentences. So that makes this conditional language modeling and such as machine translation much more interesting than language modeling. So what did I mean by saying that you all know how to build this kind of the same conditional language model, or in fact the machine translation system already? So based on all those, let's say, lab notebooks that we have released and then that you have seen during the lab sessions, you can already build a machine translation system with about 4 to 5 lines of change. This is what I always say to my students as well as my collaborators. They often take 5 times more than that, but indeed, if you try 5 lines addition, and then you can get a machine translation system. Now let's see, what are the things that we need to think about? Let's go back all the way to the very first week of the course. What did we learn? We need to think about at least 2 things, but now we need to think about 3 things. One is how we're going to parameterize this conditional distribution. Right? So conditional distribution over the answer given the input. And then 2 is how to learn. That is, that given a data set, how are we going to estimate these conditional distributions, or the parameters of the parameterization that we have used in order to compute this conditional distribution. And then the third thing that we're going to add here, because the third thing we didn't talk about that much back then when things were trivial. The third thing here is how to use this estimated conditional distribution. So in the case of learning, what do you think we're going to do? Now you know already, right? So what we're going to do is we're going to maximize the average log probability of the correct translation given the source sentence. And then what are we going to maximize it over? We're going to maximize it over the parameters that we use to compute this conditional probability. We're going to go into more detail of the parameterization. And then essentially the nice thing is that all along, we have now learned the fact that at least the modern natural language processing or the natural language generation all rely on this notion of trying to maximize the log probability of the correct answer given the input. And then that applies to these conditional language models as well. Absolutely no difference. And let's call this inference, although that's not really the best term that I want to use because it's too loaded. And then there's a problem of generation. What does that mean? Is that in the case of the classification, we could just score every possible categories to which the input belongs or input may belong. Then we pick the one with the high score. Now in our case, we actually have to solve the problem of optimization here as well. So what we're going to do is we're going to search for Y, it is the translation that's going to maximize the log probability of this translation given some X. So this is given. So this is how we're going to use a learned or the trained machine translation system. We train the machine translation system. What that means is that we now know how to compute this log probability of any translation given the source. And what we do is we're solving the optimization problem where the goal is to find Y, the translation that's going to have the highest possible log probability assigned to it. Unfortunately, as you may guess, in our setup, in particular the ones that we're going to talk about this today, we can't really solve this problem exactly. This optimization problem is really difficult. There are a number of reasons. First of all, we're going to make a very, very powerful conditional distribution, or that we're going to use a very powerful parameterization that does not assume any kind of conditional independence. So as soon as we assume some kind of independence among different variables or the different words, we can use the structure, the kind of independent structure, in order to devise a very efficient search algorithm. So we can essentially divide the whole variables into two different sets based on the independence among them, and then solve the problem here, solve the problem here separately. If there is a further independence assumption, we can go further and further, and then we can always solve the problem very efficiently. As you have guessed, the fact that we are not doing the n-gram language modeling anymore implies that we are not assuming any kind of independence. So everything is dependent on each other. So we don't have that kind of luxury of divide and conquer or the dynamic programming type of the approach to solve this exactly. Now, second issue is that this Y is a variable length sequence of discrete tokens. If we were working with a fixed dimensional continuous variable Y, then what we would do is to use all those gradient-based optimization algorithm in order to find at least the local minimum or the maximum of this log conditional probability. Unfortunately, Y is discrete. Then as we talked about, there is no relationship or the meaningful metric that is defined over these words that we can use in order to compute or define the gradient of this function with respect to Y. Now you're going to see sometimes that some papers simply say that, what if we just say Y is continuous? It's so wrong. So wrong. You should never do that unless you can actually justify mathematically if that makes sense. But in our case, that's totally nonsensical. Doesn't make any sense. Yes.
So we have the Y is discrete with tokens, but then you said we are going to be using those embeddings, which are then continuous.
But the embeddings are not tokens. So we can't turn the embedding into the correct corresponding. Can't do that portion.
I didn't quite understand why this is like different from like regular language modeling, because we could just predict tokens, right? With X and what the first token was.
Yes. So you're thinking about, so if it's an order regressive model, I'm going to solve the first one to pick the best one there.
Yeah.
And then the second given that one, so for the next one. That is if there is a nice independent structure says that the choice of the first word is not going to have detrimental effect on the choice of or the choice of the future words is not going to have any detrimental effect on the choice of the first word. That kind of assumption needs to be there. Otherwise,
but we're capturing the complexity in the original language, right?
Sir?
So we don't need to assume that they're dependent in the translated language, because we're making that prediction based on our original parent language, right?
Well, I mean, you still need to do that, right? So why is that? Because there are many different ways in which the source can be translated. And then one of those many different ways is that the same thing is showing up in a different ways, right? And then what does it mean for each of the sentence or the translations to be well formed? Is that all those words are in combination with each other in the right way. And then that right way in combination says that they are not really independent of each other. We can't really assume the conditional independence among the words in the target given source, because in fact you can do it already yourself. So it's almost like I'm going to give you one sentence that I just said, and I'm going to ask you to translate it to whatever the language you want, and then I'm going to ask you a question. What was the third word? You can't answer that one. Because you have to know what were the first two words as well as all the other words in order to exactly tell me what the third word will be. Because the choice of the other words is going to affect the choice of the third word. And then that's precisely the case. And then because of that, we can't really solve this problem exactly. I mean, we can solve it in exponential time, because the possibilities is all the possible translation is exponential. Although in this particular case, it's actually because we don't put any constraint on the length. All right, so anyway, so these are the things. But one thing that is unclear at the moment is that what is the right way to parameterize this conditional distribution? And it turned out that how to parameterize these distributions does have a lot of, let's say, consequences in terms of how good or what kind of quality machine translation system you're going to end up with. And we're going to go through up to 3 today. I don't think we'll have time to go through go into the third one, because Ilya Kulikov, one of your course assistants, insisted that I actually talk about this inference problem a bit further. But yeah, we're going to just go through the first 2 of them as an exercise, not even as an exercise, but for you to just follow through the kind of, let's say, mental steps that often these machine learning researchers they take in order to arrive at a kind of solution, to solve a problem that they run into. So, okay, so the first one, and then overall, we are always going to use the autoregressive model today. So no mask language modeling or anything, it's just autoregressive model. What that means is that the P of y given x is going to be product of t equals 1 to, let's say, I'm going to use ty to indicate the length of the target, and P of yt given y smaller than t and x. So this is the autoregressive paradigm we're going to follow. And in this case, what we need is to be able to parameterize this particular term within this product. And then because it has the kind of repeating repetition, we just parameterize it once and then use it at every time step over and over. And then let's look at what this implies. So we need to be able to compute P of yt given y smaller than t and x. And what is the input? Input is going to be, well, input is y1 all the way to yt minus 1. So this is a sequence. And then another sequence, so this is going to be concatenation. x1, x2, all the way to xtx, where the xtx is the length of the source sentence. And what is output? Output is going to be yt, which can be one of the words in the target side vocabulary. So I'm going to often just this is a vocabulary in the target side. I'm going to just use v just for the convenience from here on. So what this means is that at least from the perspective of parameterizing a model and the training a model, is still a problem of classification. Now all we need to do is to figure out what is the way in which we're going to connect these two, going from input to the target. And if you recall from the classification, essentially what we're trying to do is we're trying to compute this for function that takes as input the prefix of the translation. So what has been translated so far, that is up to the yt minus 1, and the source sentence x1 all the way to xtx, and then yt. So one possible value that the yt can take. So what could be the next translation? And then this is going to be, as usual, the bias, the scalar associated with the particular choice of the translation, next word in the translation, plus the target side embedding. So this can be considered as a class embedding of YT. Transpose, we need some function that's going to give me a d-dimensional vector, assuming that this class embedding was d-dimensional. It's going to give us a d-dimensional vector given the y1, so the prefix yt minus 1 and x1, all the xt. So when we think about any kind of parameterization for a classification problem, the first two parts are essentially fixed. Although, yeah, I'm actually writing a paper where we don't. But anyway, okay. So generally, these two are fixed. All we need to figure out is that what is the right way to summarize the input into the vector that's going to be compared against the class event. That's like the thing we need to figure out. So what we really look at is this G function. And two examples, and then the first particular case that we're going to consider is what they call a neural sequence to sequence learning, or the paper that was published by Ilya Sutskever, Oriol Pignal, and Paul Lee in 2014. And I'll just call it Sutskever. This is a conference when Ilya was giving a talk, and at the end of the talk, he declared that the machine learning was solved. But he has been doing that like every now and then. So but it was a pretty dramatic moment. So we're going to now think about it from the perspective of encoder and decoder in this particular case. So we're going to look at encoder and decoder. I actually had almost same paper in another conference, but I didn't declare a machine learning to be solved. So no one really remembers the same paper. So what is the lesson? Always be a hyperbole? No, don't be like that. But anyway, all right. So we're going to think about it from the angle of the encoder and decoder. It is a pretty natural way to think about it because we have a source sentence that we need to encode into some kind of code. There is a vector representation in the middle of the neural network. And then we need a decoder that's going to decode out the translation out of this code that we have. Right? So we're going to think about the encoder first. In this case, encoder is a unidirectional LSTM network. Just like the one that we have used or seen from the left section on the recurrent language model. So there you saw that, with the LSTM, we can just train a language model without too much issue, unlike with the vanilla recurrent network where we use the hyperbolic convolution. So we do the exactly same thing on the encoder side, except for the fact that we are not going to predict any of the words in the source sentence, because that's not what we're trying to compute. We're trying to compute whether we can predict one of the target words given the source and the prefix of the translation. So in this case, in the encoder, it just reads. So this LSTM network is going to read the source sentence X one word at a time. Then now how we encode each source token, we're going to use the embedding, right? This is E. And then this is for all, let's say, T from 1 all the way to Tx. So we are going to embed it first. So we have the sequence of tokens. So we embed them first. We now have a sequence of continuous vectors. And then this sequence of continuous vectors, so Ex1, Ex2, Extx. The sequence of the vector is going to go into LSTM. Let's say the first layer. Let's call it LSTM box. And then what will be the very initial hidden state? We have to decide. We can just put all zeros, right? All zeros. And then it's going to give me the updated cell state and the output. And then that's going to go into the next time step where the exactly same LSTM is going to be used now with the hidden state coming out or cell state coming out of the previous time step and the new the embedding of the new next word. Then it just continues on and on until the final one is written. And then the output from here, either the cell state or the hidden state, you're going to just refer to it as H, let's say 1 Tx. So it's going to be just a concatenation of the cell state as well as the hidden state. Right? The LSTM has a bit of a weird way to separate those two. And then you can imagine that we can do the exactly same thing for multiple layers. And then let's say we have the capital L many such layers. Now, only thing that changes in those many layers is that the now input to the any deeper layers is not the actual input or the embedding of the source tokens, but the hidden state and the cell state that is output from the previous LSTM layer. Now, one thing is that we're not going to share the parameters of this LSTM across layers. We're going to use a different set of parameters for each individual layer. Then we end up with the, let's say HLTX. So we get a bunch of vectors. And then you can imagine, you can think of this sequence of vectors as the actual code, or the encoding of the source sentence. Okay? So what this encoder did was to read the first word, get the hidden state, and then given that, read the second word, get the hidden state. And then if you recall from our language model lecture or the recurrent language model lecture, these things are essentially summarizing the source sentence one word at a time in order to, while preserving, in order to maximize the amount of information that is preserved from the source sentence, in order to maximize the quality of predicting the translation. So at the end of the day, this is a pretty nice summary for the code or the encoding of the source sentence for the purpose of machine translation. Yes. So that was the encoder. Now the next turn is the decoder. Now decoder is also going to be an LSTM network that's almost same type. Then this is also a unidirectional. And then if you think about it, it shouldn't look any different from the encoder. So let's say, because we are assuming that we are given some prefix, right? So y1, y2, all the way to yt minus 1. And then what that means is that we're going to have the embedding of y1, y2, yt minus 1. And then we're going to have the LSTM network. Again, the L many layers, I'm going to say that is going to look exactly same as the encoder. Then this LSTM is supposed to read this prefix. So what has been translated so far. And then what does it do? It summarizes this, what has been translated so far, so as to maximize the prediction of the following one. But then the question here is, how are we going to initialize the hidden state? In the case of encoder, we said that, okay, there's nothing before. So we're going to initialize the cell state as well as the hidden state to be all zeros. But now, in the case of the decoder, one thing that needs to be done about decoder is that the decoder cannot simply summarize the target prefix. It has to summarize the target prefix as well as the entire source sentence. So the idea is to copy over this entire thing. So the hidden state and the cell state that comes out of the encoder, and then use that as the initialization of decoder's LSTM. And thereby, what this concatenation of these two LSTMs, so the encoder and decoder, what it does is that it's going to summarize the source sentence and then continues on to summarize the prefix of translation. And then once we have all these summaries, what we're going to do is take the very final one. So let's call this Z, L, T, minus one, yeah, T. And then we will code this vector to be the output from this G vector, G function. And then what do we do? We're going to compare this ZTL, this final vector that we get out of the concatenation of the encoder and decoder, compare that against the class embedding or the word embedding of the target word, each and every one of them, that is added together with all these bias factors, and then that's going to be our score. So this is the output of G of x1 all the way to xtx, and then y1 all the way to y minus. And then as we talked about, once we know how to turn the input into a vector, from there everything is very standard. It's just a linear classifier on top. So this looks pretty simple, right? But this is how we actually solve the problem. Is that we have, and then we have the input, and then we have the output. Now what we need to do is to make sure that all the information from the input is going to be summarized into a single vector eventually for us to be able to predict or to score all possible outputs, right? And then in this particular case of the autoregressive model with the LSTM, the nice thing is that we can in fact use the very same decoder and the encoder just one step at a time in order to get this output from the G function for every time step as we read the target sentence, one or the other. So we can just process the whole thing in linear time with respect to the length of the source and target. And this is really like how people solve these problems of the complicated mapping between the input and output. Yes.
Do we really need to? Can we just concatenate this sentence and that, and just pass it to one of those layers?
Oh yeah, good question. So are there actually two neural networks, or can there be just one? Now that's a really interesting thing. Is that are there actually two neural networks, or is there just one neural network, or is there two element in neural networks?
You can just use one of the blocks, right? The
You could very well do that, but does each and every block need to be the same thing? Should it be different? Those are the choices that you need to make, and then you just need to be able to justify all those choices. As long as you can justify why you do so, in fact, you can be as free as possible in how you build these instruments, right? So in this particular case, what the Ilias team did was to use the same set of parameters between the encoder and decoder, but each layer of the LSTM had a different parameters from each other. And then essentially the very rough justification there would be that the languages do tend to share a very common structure across the different languages. But then the layers represents the different levels of the abstraction, and then if you think about it, probably makes sense to use different, let's say, mechanism to process different levels of abstraction. So there was a kind of reason, but obviously those are not really the major reason. What is the major thing here is that the LSTM is known to capture all those long-range dependencies. And then for translation as well as the language modeling, we know that it's important to capture all these long-range dependencies. For machine translation, even more so, because we have to capture the long-range dependency that goes across the boundaries of two different languages. And then the nice thing about the LSTM or the recurrent network in general is that the processing time is linear with respect to the length of the sequence. And that is pretty advantageous, especially in the time of testing. During the training, yes and no, but during the testing, because we don't really have these words in advance, we need to predict one word at a time and try to predict it, and that can be a bit taxing. Right? So those are actually a better reason. Now this one actually worked pretty well, but then this one had one kind of particular, let's say, disadvantage is that the encoder had a pretty huge burden of having to compress the content of the entire source sentence into a fixed size vector. So however many layers you have, however, let's say, wide each of the layer is, still fixed size. Then if you think about, let's say, compression in general, you probably use, let's say, tar, zip, or there's a zip or whatnot, right? You're going to find it really, really weird if your compressor is always returning the file, the compressed file that has the same length, regardless of what the original file size was. In fact, it just feels very natural to imagine that the encoding of the input or the file that you want to compress should be at least proportional to the size of the input. No, it doesn't have to, because the size doesn't really tell you the amount of the information it contains. But you can imagine that the size of the input is the upper bound on the amount of information that can be encoded within them, so within that input. But here, that is not the case, right? Here, everything, the encoder is asked to essentially encode the entire source sentence, regardless of how long, how short, how information flow rich, or the information for the source sentences. It has to just compress it into a single finite spectrum. That turned out to be actually quite problematic. And then what we could see back then was that if you make a really, really large model, this tended to work reasonably well. But as soon as you make this model even slightly smaller, then this model, this approach should kind of, let's say, fail to translate a long sentence. Could still translate the short sentences pretty well, but for long sentences, this approach started to fail. So then, can we actually do better? And then we already learned how to do it better, but we're going to just follow some kind of, let's say, historical route. We're going to go into the next paper, next approach. It is based on the Dima, Banana, Lee, and Joshua Bengio's paper in 2014. The 2014 was a pretty interesting time. GANs were all invented in the same place. It was fun time. Anyway, so let's move on to the next one. So we identified some issue with the original Suskever et al. Model, and then there were actually a couple of the papers in between this Suskever et al. And Banana et al. Where we just identified those issues, and then trying to figure out what are the ways in which we can solve it. And then there are a number of, let's say, ways to tackle it. One is to consider the sequence-to-sequence translation model, the Suskever et al. One, as a phrase-based translation system, and then use the outcomes from these models and then combine them in a way that makes sense. That one worked well, but that one did not give us the fluent translation, because the fluency of generated text comes from the fact that we use a neural network that has no bound on the context that you can take into account. On the other hand, as soon as we start translating at the phrase level, we already put a huge, let's say, constraint, or we're assuming a pretty severe Markov property, saying that, when we make a translation of this chunk, we're going to only look at the particular chunk. So that would never give us a fluent enough translation. So instead, we had to be a bit, in that case, what we are saying is that we want to preserve this property. So what we do with the learning, right? Essentially, we want to preserve this part. That is how we're going to estimate these conditional probabilities and how we're going to solve this inference. That is that we're going to actually have a single conditional probability distribution, probability that we're going to maximize. Unlike the, let's say, phrase-based one that I just briefly described, where we're going to just divide it into different chunks and then translate them separately and then they combine them together. We're not going to do that. So then the only thing that we can actually do here is to change the parameterization. So that's kind of, let's say, the thing is that whenever you're trying to solve some problem with the machine learning, you've got to think about all three aspects at least. Of course, the fourth aspect that is often most important is how you actually have collected and prepared your data. That actually changes most. But that aside, assuming that you have worked with the domain experts who can actually give you the advices on what kind of data is available and how those data is clean, noisy, if noisy, in what sense, then once you know all those things, and you think about can we come up with a better learning objective function? Or can we come up with a better learning reward? Can we actually use a already trained model or the estimated conditional distributions better? Can I actually regularize the trained model when I use it for this? But then the third thing is the parameterization. And back then we knew that the whole fluency of the generated text comes from the fact that we actually do not assume any of those independence among all those words. We really couldn't touch any of these. And in reality, we do touch them, but not those that introduce more independence. So then we had to go with, we then go into the parameterization. Let's look at what kind of things we can do in order to improve this. So in the case, so I'm going to just follow what this paper did back then. Again, we're going to stick with this the concept of encoder and decoder. So the encoder is going to encode the source sentence. In this case, the encoder is going to be bidirectional. We use gated return units, but could very well use the LSTM without any changes. And then what we do is that, of course, one thing that we are not going to change is that we're going to use the continuous embedding of the source sentence. So we have so we embed each and every source word. And then I'm going to just assume that we're going to have just one layer, because as you saw, multiple layers, the same thing, you just do the same thing over and over. Let's say I call it GRU, let's say you are the forward. So the forward gated recurrent unit is going to read one word at a time from left to right. And then we will have a backward or the reverse gated recurrent unit. That's going to read the same sequence, but from right to left. Here. So it's just bidirectional because it's almost a joke to call it a bidirectional in the sense that we just have two GRUs, right? Two recurrent nets. And then what we do is that on the one side we send the sequence as it is. On the other side, we're going to just flip the order, then send it. And then we're going to just flip back the vectors. But what we are going to do is we're not going to look at the final hidden vectors only. So we're not going to look at this one only. But we are in fact going to look at all the hidden vectors. So for the x1, we can concatenate the hidden states of the forward and reverse gated recurrent units or the recurrent units. And then say that, okay, that's going to be our encoding of the first word in the context of the entire source. Then we do the same thing for each and every word, resulting in HT, H1, H2, and HTX. So we're going to concatenate the hidden state of this recurrent neural network, two recurrent networks, one forward and the other one reverse, and then say that so instead of using just the final ones, why don't we use the entire set of these concatenated or context-dependent word vectors as the representation of the source. Now, this is a pretty major departure from what the Suskever did, in the sense that now the encoding of the source sentence adapts its size according to the length of the source sentence. If the source sentence is long, which means that there is a chance that there could be more information embedded in it, we're going to encode it into a much longer or the larger set of vectors. If the source sentence was shorter, then we're going to say, we're going to use a fewer hidden vectors to encode the source sentence. And then the decoder is a unidirectional. It's a GRU, so we use GRU, but again, it could very well be LSTM, or could very well be just a vanilla recurrent network. Although, using a vanilla recurrent neural network where you use instead of GRU or LSTM, the hyperbolic tangent units followed by, actually the affine transformation followed by the hyperbolic tangent unit is always a horrible idea. I think I wasted about 8 months of my post a fellowship, on just trying the whole thing with the hyperbolic time unit. So, and then it just never worked. All we had to do was switch it to a GRU or LSTM. No one told me back then. Now you're lucky, you know what to do. So here, now what do we have? We now again have this sequence of the embedding of the prefix. So what has been translated so far. So we now have the embeddings of the words that have been translated or the generated as part of the translation so far. And we are going to look at this final step in particular. So we have the unidirectional GRU here that's going to read one word at a time until this point. So we do have here, let's call it ZT minus 1. ZT minus 1. So we have, what do we have? We have ZT minus 1, we have E of YT minus 1, and we have all these vectors coming out of the H1, H2, all the way to HT. And this is where the whole concept of attention actually came out. What is the right way to update this CT minus 1 so as to we summarize all those sentences so far and then the new word in the target site that's going to be added? It turned out that the attention is the particular way to do so. And then in this Badenauer 2014, what we did was to use so-called content-based attention. Of course, we didn't even call it attention, we didn't call it content-based. It sounds pretty nice. And I think always you try to make an algorithm that others are going to name, rather than you try to name it too hard, and then you end up with all those ridiculous names. So that's I think one of the ways in which you can tell that whether the algorithm is being used or not. But anyway, so here we're going to introduce the attention. And then this attention is going to be a function of previous hidden state CT minus 1 and the current input embedding of the YT minus 1 and all those hidden vectors coming out of the source. The first step, and then here, what I mean by content-based attention is that the key, value, and query vectors are all the same. So we're going to just use a single vector for key, query, and value. So first step, we're going to mix the new input, so the embedding of the YT minus 1 and ZT minus 1 into a query vector. Query vector is going to be some function, and I'm going to call it mix here. Could vary or be just a multi-layer perceptron, linear combination, or whatnot. Mix of the E of YT minus 1 and ZT minus 1. Second step, we simply say that the so sorry about that. So we're going to say that the value as well as key vectors of the previous, let's say, items that we're going to append over. So what we're going to append over is the H1, H2, HTX is simply going to be those values themselves. Okay, so where the T prime goes from 1 to capital TX. We now know how to compute the attention score. So the attention score for each one of these. So the attention score is associated with each and every one of these source side hidden vectors that represent the input. So the alpha T prime is going to be proportional to the x of the dot product between Q and key of that particular T prime. Now, what is this proportional to an exit? That's just solve. And then this happens for all T prime going from 1 to T. And once that's done, what we're going to compute is that we're going to say, let's call it Z tilde T. So this is going to be the summary that we get out of the source sentence given the current context, right? So what has been translated so far, that is the weighted sum or the convex sum convex sum of all the source side hidden vectors, so ht prime, with the weights that are given by this alpha t prime. This is just like the attention that we learned. Only thing that is different is that we are not separating out the value in t, and we are not attending over what has been generated, what has been coming out of the current, let's say, sequence, but we're attending over the source side vectors. So some people started to call it cross attention, but yeah, people are just naming to this stuff. It's impossible to tell what they're doing. But once now we have this z tilde t, that is what comes out of this attention. What we now need to do is we need to feed it into gated recurrent unit. So z tilde t, and then we want to feed it in z t minus 1 as well. And then it looks at the input and gives us the mu zt. Right, so really like the decoder's GRU takes as the input, not two things. So that's the usual thing. There is the input and the previous hidden state. But this one is going to take as input three things. One is the input, the time step, previous hidden state, as usual. The third one is going to be this z tilde t that comes out. There is a convex combination of the source side vectors where the weights were determined using this mechanism of potential. So what do we do with the three inputs instead of the two inputs, right? We just need to combine those two inputs that is not hidden state into a single vector, right? Using a multilinear perceptron or whatever. Once that is on, what do we do? Once we have this zt is precisely the g of x1 all the way to xtx and y1 all the way to yt minus 1. From here on, everything is standard. We compare this vector using dot product against the class embedding, that is a target side word embedding, to get the score after adding the bias. And then this is how you end up with the slightly better version than the original version that was proposed by the Suskever. So what has changed? The first thing that has changed that is most apparent is that now we encode the source sentence into a representation whose size depends on the size of the, that's a major difference. But there is another difference that is probably even more major or the more consequential, but it's not too visible from here, but we already learned about it, is that the computational complexity, the change in the computational complexity, we essentially go one level up. So here, let's say when I try to compute the score of the target translation, what is the computational complexity with respect to the length of the entire thing? There's a source and the target. It's linear with respect to the length, right? So what it means is that the problem that can be solved by this approach is a problem that requires linear or sublinear time with respect to the length of the source sentence, and also the target sentence has a similar length, so that's just constant. So that is the kind of the specific assumption we're making here. On the other hand, if you look at this Badenau and then in particular this attention mode, we are making comparison against each vector in the decoder side against all the vectors in the source. What that means is that the computational complexity of this approach is not anymore linear with respect to the length, but it is quadratic, so the square of the length. And then that dramatically increases the size of the problems that can be solved. So however big we build this original network, if the problem requires the computational complexity of O(n) square or n cube, cancel. There will always be an instance that cannot be answered correctly by this approach. On the other hand, this one kind of increases that family of problems that can be solved by 2D ON square or the OT square, right? Where the square corresponds to the length. The T corresponds to it. Yes.
What's the thought process behind taking a bidirectional GRUs?
Oh yeah, so the reason why we take a bidirectional version, by the way, yeah, that's not like absolutely necessary, but it actually makes learning so much easier, is that what does each of these vectors corresponds to? What is the thing that we wanted to encode? What we wanted to encode is the semantics of this word, but the semantics or the meaning of this word within this context, within this sentence. So it was just natural to think of this H2 as the hidden vector that comes out of reading the preceding words and also the following words. So, like in some sense, this approach is kind of, pretty much more strong, much stronger than the first approach. Although, what this means is that and can we actually make it even more powerful by having more and more of these attention layers, and then that's how you end up with transformers in 2017. So instead of looking at the recurrent network, we're going to use the self-attention over and over, together with the cross-attention, because we're going to do the translations, and then add in the positional embedding, and we end up with the transformers. But as you can see, the transformers may have some weakness, right? Just thinking about it from this angle, the computational complexity or what can be computed is that the transformers, the amount of the computation that is done for each of the token in the source side or the target side, the amount of computation that is being done, except for the summation that comes from the solve factor operation in the attention weight score normalization part, is in fact finite, is fixed, is constant. So the one thing that transformers can't do is counting. So you can't really count how many times the words appear in the source and target. And then it turned out to be reasonably okay when we work with like naturally occurring text, because we rarely actually write the same thing over and over. And then you say that, oh, I said some, this word message 25 times or something like this. So that's fine. But generally, that's just an example of what we need to think of when we're trying to come up with this kind of parameterization. What are the things that are needed in order to solve a problem? Difficult instances of the problem. And then what are the computational complexity or the memory complexity that is required for those difficult instances to be solved? And then often we don't know, because the problems that we solve are the problems that we don't know how to solve, which naturally implies that we don't know what the complexity is. But there are a few aspects that we know that our parameterization needs to do. For instance, if the problem requires that we need to count, then using recurrent net is always a good idea. If the problem requires that we need to attend to all those places over and over in a quadratic time, having attention is necessary. If the problem requires, let's say, cubic time, right? So looking at this kind of, let's say, higher order interaction, then we need to think about something more. And then there are many different approaches, such as the universal transformers or the neural GPU, all those different things, but they are often not theoretically interesting, but practically not so much. That said, we're going to take a 5 minutes break. We'll come back at 6:12 and continue with the inference part. Yeah, also, I think except for the summation, the soft-text normalization, now if we look at how many nonlinear computations that is done between the input, then the number is actually constant. It doesn't grow even if you have many unknown sequences. That's what Why don't you ask me? It's going to be a question that a lot of students are going to. Yeah, you can ask a question.
Like no layers versus like just like one layer.
So think about the idea why we discussed earlier that the linear layers are needed. So the linear layers are not powerful enough to capture the higher order interactions, and having more linear layers will allow you to capture more even higher order interactions. And then you should ask a question during the lecture so that you can answer that.
It's like this first so like has
Yeah.
Sorry.
This is just literally mixing these two. But it's the value and all right. Okay. All right. So before we continue, any questions? What was the question?
I was asking how dependent are the internal representations on the output language, and you can describe the encoder and decoder.
Right. So the question is, what do these vectors look like essentially? And that applies here as well. And then that applies to everywhere we have this kind of nonlinear layers. And then what do those vectors look like is that they don't look like anything. That's the most important thing, is that you shouldn't actually read too much into this hidden representation or the activation vectors, because there's always the ambiguity. Ambiguity arising from the fact that there are a lot of symmetry in our neural network parameterization. What is the symmetry? Let's say I have one hidden layer, a classifier that has one nonlinear hidden layer. Now what I can do is that I can just permute the rows or the columns of the weight matrix in the first layer, and then permute the bias vectors, the dimensions of the bias vector, and then permute the output weight matrix accordingly. And then everything looks exactly the same from the perspective of what is being computed by this classifier. However, when you look at those hidden vectors, they're going to look ridiculously different. And then that actually is one of the simplest possible symmetry, but there are so many different types of the symmetry. So let's say I'm using the rectified linear unit. It's just a linear function at the end of the day, it's a piecewise linear function. Let's say I decided to flip the sign of all the incoming weights in the incoming weights, but then what I'm going to do is I'm going to flip the sign of the outgoing weights. Then suddenly the function is exactly the same, but then what is being computed can change out. The vector itself is going to look very, very different. And then there are so many different types of the symmetries that can be discrete and also continuous as well. And there is a reason why we shouldn't really read too much into all these internal vector representation, how they look like, let's do TC and whatnot, because they don't really often really much. It's almost like reading million P. You can read whatever. You're going to see tigers, you're going to see dragons, you're going to see the future bride of yours, or your future the partner, future kids, future grandkids. Whatever you want to see, you'll see. And it's a very high dimensional space. And then in that kind of high dimensional space, you can really see everything. So that's the reason why we never, at least in this course, we don't really talk too much about what things are. Although later in the course, if the time permits, and as far as I can tell, time is going to be there. One thing, I'm going to spend actually one lecture to talk about these symmetries and ambiguities in the deep learning and how those are actually leading us to some troubles when trying to solve the problems that are, tricky, put it like that. Well, we'll get to that in a few weeks. Now, that said, Ilya, my PhD student, of course, assistant, really insisted that I talk about this inference problem, so we'll have to actually get to that one. So let's call it generation. So what we have just learned is how to build a neural net that is able to compute this low probability of translation given a source set. So we now know how to compute this. If somebody gave you a pair of source and this translation, you can now ask your model how probable that translation Y is given the source sentence. And what that means is that if you are given only the source sentence, you just need to solve the problem of so-called arguments. Where I'm going to use the L to denote a set of, excuse me, set of all possible translations. Excuse me, yeah. So, how do we solve this? Excuse me. Sorry about that. It's just sorry. For condition. What's a lot? 2 minutes. 2 minutes. Sorry about that. This just happens once in a while. But anyway, so how are we going to solve this? Any thoughts? Well, you know how to compute this one. So how do we solve this problem?
Yep. So pick the maximum. So how?
Just generate y, and that'll be the maximum anyways.
We generate y from where?
The data like we did before. For x.
Oh, so the x is the new x that we haven't seen yet. So we just wrote a new sentence, and then we are trying to see what is a translation that's going to maximize this score. So how do we solve this problem?
Doing some sort of a search on y.
Uh-huh.
So we can pick a y and then pick the next y and look at the probabilities of both of them and then pick the one that maximizes.
Very good. Okay, so we start from some y. Then we choose the next y. Let's see if the next y has a higher probability, then we're going to keep that one. So how do we choose the next y?
We need to feed it into the decoder and get the next set of probability distribution.
Oh, I see. So you're thinking about this kind of autoregressive model. So that's good. Let me see. I'm going to copy it over. Let's see. Copy. So what you just told me is that so since this probability over the y, the translation, can be written down as the product of the next word probability. And then what this actually implies that we have decided that there is a particular chain-like structure. So each and every one of these is a random variable all the way until yt, say ty. And then we're saying that the y2 is conditioned on y1, y3 is conditioned on y2 and y1, and then yty is going to be conditioned on everything before. And then in this particular case, we know how to sample from this distribution exactly. And that's called the ancestral sampling. So we're going to sample from the distribution over y1. And then given that, we're going to sample from y2. Given these two, we're going to sample from y3. And then continue all the way until we end at the very end, let's say variable. So it is but that's sampling, right? And then we just talked about earlier today that these probabilities in this combinatorial space don't really make much sense. What that means is that the sampling from that distribution, which is described or characterized by those meaningless probabilities, probably are not going to be the ones that correspond to the kind of our notion of the valid samples or the translations. So instead, what you just proposed is that instead of sample, can we simply take the most likely y1, given this conditional distribution over y1 given x, right? So we have the x. And then once that's selected, we're going to go into the conditional distribution over y2 given y1 and x, and then pick the one that is most likely under that one, and then we continue all the way. Now, that is called a greedy search or the greedy decoding. In this greedy decoding, yt hat is the argmax. So yt within the vocabulary. So we're looking at one word at a time. Given of the log probability of yt, given all the previous one that has been already decoded or selected, nx. And this is suddenly now much more tractable than before, because it only takes us linear time with respect to the length of the sequence, or the linear number of the optimization problem, where each optimization problem requires us only the constant time, because we just need to check all possible unique target words. Unfortunately, it turned out that the sequence we get out of this it's not necessarily the max, or does not necessarily maximize this low conditional probability of y given x. So why is that the case? Why is that the case? The reason why that is the case is precisely of what we discussed about the lack of independence assumptions. So it looks like if we just without thinking, it looks like just looking at these arrows. It almost looks like whatever the choice we make here is what influences all the other future choices, but not the other way around. Unfortunately, that's not really the true case. What we do in the future, in fact, changes what is the optimal choice in the past as well. Why is that? Why is that the case? Why is that the case? So then what did this the arrow actually mean? So when this arrow seems to indicate that what we do in the past influences the future, but what does it have to do with future choice influencing the past? Either too obvious or too confusing. I'm not sure. Which side are you on?
It kind of makes sense because what we want to express, like we choose our initial words, like based on what we want to finally express, right?
Okay.
So it kind of depends on the future words. Like, how we choose our-
Yeah. So my question was more like, why is that the case? So how does that actually agree with these arrows that we have there?
I guess we are looking only in one direction, unidirectional context to generate the future words. So since we were even in encoder, we were considering both directions. So even during the generation time, I guess we should consider
I
the.
see. Yes, yes. So because we're making a decision based only on the partial information, so it's kind of inevitable that our estimation of what is the most likely word, it could be wrong, right? So that could be a wrong way to think about it. But it turned out that the answer is actually so much more dull. In a sense, in this kind of, let's say, statistical modeling perspective, this probabilistic graphical model, these arrows here, are not actually telling us the direction of influence, but more of our choice of movement. Is that these arrows actually tell us, only thing that these arrows tell us, or there are two things that arrows tell us. One is that to define a distribution over all these variables, each and every arrow corresponds to the conditional distribution, or all the incoming arrow for each of the variable defines what are the other variables on which the conditional distribution over this particular node or the random variable depend on for me to write the joint distribution eventually. So that's what it says. Now, the second thing is that, of course, if we don't have all these arrows, and then we can actually express the independence properties. But as soon as there is an arrow, the direction of the arrow is actually my arbitrary choice for the purpose of model. The direction of the arrow, so the lack of the arrow, independence. So no direct dependence between two nodes. But the existence of the arrow tells me only that these two nodes are not statistically independent, at least directly, right? But the direction doesn't really tell me anything. Direction is nothing that is inherent. It is the choice that I make. Is that how am I going to define the joint distribution over these variables? What are the conditional distributions that I'm going to use to describe this joint distribution? And what that means is that when we think about all these, let's say, conditional dependencies or dependencies, we shouldn't just follow the arrow direction, but we need to follow the principle of so-called deseparation. So according to deseparation, or there is a set of rules that we can follow, and then we can actually tell, given any directed acyclic graph like this, we can now tell whether any given pair of the random variables are independent of each other. And in this particular case, it turned out that every pair of random variables you choose, they are statistically dependent on each other. In other words, the choice of the y, take y1 and the y, they are statistically dependent on each other. Again, statistical dependency does not have the arrow. There is no direction. You can always flip it. How do you flip it? Using Bayes' rule. So what that means is that the fact that there exists a statistical dependence between, let's say, y1 and all the other variables, so that is that the future words are conditioned on the past words. In this particular case, also implies that the past words are all dependent upon the future word. So we can't really choose the optimal choice of the word without knowing exactly what all the other words have been selected. And that is the reason why it's a very difficult problem to solve. And then there is a reason why greedy decoding is not going to be the solution here, because we make a decision every time without looking at the future words. Now, can we do a bit better than greedy search? I guess so, right? So what would be one kind of thing that you notice about greedy decoding is that we always commit to our choice at every time step. We always commit to the choice that we make at the time step. What that means is that we're going to make a decision without taking into account any possible future changes. So how will we actually do it? It turned out the simplest way is that you don't commit to one decision, but you're going to carry over multiple possible good solutions to the next step. And then that leads to what we call beam search. So beam search is a very natural generalization of greedy decoding, where at each time step, instead of taking the arg max, we're going to take the arg top k. So what do I mean by the arg top k is that I'm going to look at the top k possible continuations or the prefixes, because everything is prefix, right? So y hat t implies that I have y hat 1 all the way to y hat t minus 1. So this is actually just looking at how to continue the prefix into a slightly longer prefix. So we're going to do the same thing here. But what we do here is a bit tricky. It's quite tricky. So what we do is that we're going to look at the prefixes that we have collected so far. So we have prefixes that we have collected so far. Let's say we have k of them already. Now this is confusing, but well, bear with me. So we have k of them. So there is 1, 2, let's say capital K. So we have, these are the index for the prefix that we have carried over so far. So we don't carry over just one. If we did that, that becomes greedy search. What we do is that we're going to carry always k possible, let's say prefixes. Let's carry k possible prefixes. And then for each prefix, what we have is that we have, let's say, the vocabulary. Let's use that. It goes from 1 all the way to the size of vocabulary. So we're going to consider all k hypotheses, hypothetical prefixes that we have carried over. And then for each one of them, we're going to consider each and every possible way to expand this. So we have the k times the size of the vocabulary, many possible candidates, right? So we have the k many hypotheses I have carried over. Each one of them is going to be expanded by the size of the vocabulary. So I end up with the vocabulary size times the k, the number of the hypotheses that I carry over, beam search is going to carry over. And what we do is we are going to look at all those continuation and score each and every one of them. How do I score them? Is to look at the log probability of y smaller than t hat k. So that's going to be the k hypothesis. So I have the score so far. What is this score? It's going to be the sum of the log probabilities of all those words in each of the hypotheses plus log, so let's put ik actually, log p of y, yt equals I, just I is fine. AI, so we're doing the joint optimization here, given the y hat k smaller than t and x. So this is the score of the hypothesis that we have carried over so far. And then this is the score that is added for the particular expansion. So given this hypothesis, now I'm going to expand it with the first word, second word, third word, all the way to all the words that I have in the vocabulary. And then I now get a score for each and every possible continuation. And then among them, I'm going to pick the top k of them. And then the top k is going to be my next steps, k hypothesis, hypothetical prefixes I carry over. So it's going to be y smaller than or equal to t, 1 all the way to yk smaller than or equal to t. So this is what we're going to get. And then we apply it over and over until all these prefixes or their prefixes complete. How do we know that it has completed, or each one of them has completed? When this ends with the special symbol, end of sequence. You have already learned the sequence, symbol. As soon as the symbol is met, we say that our search is over for the particular hypothesis. We're going to drop it from this. Continue with the k minus 1 of them. We do it over and over until we exhaust all the themes that we have. And then how do we choose one of them? We choose one of them not based on the final token score, but based on the entire, let's say, sequence score. And that's beam search. And then what does it actually tell us is that it tells us that they do not commit to a single decision to all. And then that's generally a good advice for not only for machine translation system, but for life, is that you try to carry over as many options as possible, as long as they are viable. So that's the reason why you can't carry over all possible options. You keep some of the important ones, and then only time you want to make the commitment is at the very end. Once you have gathered all those evidences, right? The evidence is the scores that you're going to collect, and then at the very end, you accumulate all those evidence for each of the possible choices, key main choices. You choose someone with the highest score. So that's going to be beam search. Now, when does the beam search become exact? Beam search is exact when this k is infinity. When k is the size of the vocabulary, that's still not exact, because the number of the hypotheses that you need to consider grows exponentially as you continue on in this search. So essentially, effectively, the size of k needs to be infinitely large in order for this algorithm to be exact. And another property of the beam search is that it's an inexact search, and it's also not complete, in a sense that the beam search with k equals 5 is not guaranteed to be better than beam search with k equals 4. So increasing k, so the quality of the search that is determined by the log probability of the found, the resulting sequence does not increase monotonically with respect to the size of your beam. That's a bit of an unfortunate thing about beam search, is that if we had that kind of guarantee, it would have been so much better. But we really don't have that guarantee. Now, we can always turn that into a version with a guarantee, is that every time we run beam search with beam size k, we just do the beam search with the beam size 1, 2, 3, 4, all the way to k, and then pick the one that is best. Then we're guaranteed that it's going to not get worse, even though as we increase the k, but that kind of defeats the whole purpose of the computational efficiency. So in reality, what we often do is to choose the K based on the validation set. So we use a validation set to choose K to maximize the validation score, just like what we talked about at the very beginning of this course. So K is a hyperparameter, although it's very unclear why I think K should be a hyperparameter here. I think we should be able to come up with a better search algorithm in general. All right, let's see, what's the time? I'm almost there, but now the implementation-wise, beam search is actually one of the algorithms where everyone makes mistake implementing it. And then every time you implement it, you're going to have some mistake. So my suggestion is to just use the off-the-shelf beam search algorithm instrumentation. Quite a lot of them are there. But you can always improve the computational efficiency by carefully implementing it yourself. All right, so this was the inference part that I should have covered. One last thing that you're also asking me to cover is pretty demanding as a course assistant. Is that let's just think about one very particular case here. Let's just look at this one. Well, actually, yeah, okay. Let's look at this one. It doesn't really matter what kind of parameterization you use. Now, when you look at this problem, you should actually immediately start noticing that there is something weird going on. What is that weird thing? If I gave you any translation except for the very final word or the last two words, and also without the source sentence, would you be able to complete the translation? Almost always answer is yes. So what that actually tells us is that as we go back and back into toward the near the end of the translation, the chance that we can predict what the next word is going to be in the translation without looking at the source sentence goes up. Because we have enough context coming out of the translation itself. So what does that mean is that there is a weird ambiguity that exists in the problem of machine translation, or generally in the problem of conditional autoregressive language model, or the conditional language model in general. It's because the target, so our target is sentence has a high degree of statistical dependence. There are a lot of cues that our neural network can use to predict the next word without looking at the source. And the funny thing is, the same thing can happen in the other way around as well. Sometimes you should determine the next word based on the grammar or some kind of target language specific properties. But then the neural net might as well just look at the source and decide to use a particular word. Because source also provides a lot of context. And this is a problem even the infinite amount of data does not necessarily solve. Because there could be a case where those two cues, the cues coming out of the source and the cues coming out of the target context, are just almost always there. Now imagine a case where, until let's say I went to Rwanda in 2018. Was it 18 or 19? 18. 18. I didn't know that the people were eating the green bananas, right? So bananas are all yellow, at least to me. So in my vocabulary, that is pretty much the complete vocabulary, the knowledge about the Korean language. The bananas are always yellow, right? But then in that case, and in my mind, the bananas are also yellow. Like the Korean, it's also yellow bananas. So if I gave my knowledge of all these translations or the examples, then my translation system might choose to look at, well, there was yellow, let's say banana, or there was a yellow in the source, banana in the source, let's say banana. That's a kind of genuine ambiguity. So what that means is that even if we train a model really, really well, each and every model we train may actually behave differently when there are the kind of symmetry or the ambiguity in the data itself. And that actually makes it difficult for us to also determine what are the things that we should expect from these internal vectors as well. So it comes all the way back to the question that you asked earlier, is that what does this neural net do, and then what should they do? We actually don't know. Because those symmetry or the ambiguity in the data, we don't know what kind of things exist. If we knew, then we wouldn't do machine learning, we would just write down the approved models. But yeah, so I don't know why Ilya wanted me to talk about it. I did, so hopefully that's all fine with him now. So as usual, lab sessions tomorrow and day after, and I'll try to unload everything as quickly as possible. And apologies for the throw thing. I just enjoy my life a lot, and because of that, I had a number of the health issues earlier, and this is one of the kind of the thing that I have to suffer because I enjoy my life. Anyway, well, that's it. I thought it was going to be a bit shorter lecture, but it's actually the full time. All right, have a nice evening.